Okay, guys, this is going to be the last video that covers the remaining questions for this final exam review for Math 1342. So let's go ahead and jump in. All right. So this question says, classify the hypothesis test as two-tailed, left-tailed, or right-tailed. So we have to read the scenario to see what we're dealing with. And if I need to draw anything on the screen, I'll go ahead and draw any sort of visual aids if it's going to be useful. Okay. So this question says, at one school, the average amount of time that 10th graders spend watching television each week is 23.1 hours. Sorry, 21.3 hours. Dyslexia there for a moment. The principal introduces a campaign to encourage the students to watch less television. So right there, we want to introduce a campaign to get the students to watch less television. 1 year later, the principal wants to perform a hypothesis test to determine whether the average amount of time spent watching television per week has decreased from the previous mean. Okay, so if we're looking at a decrease, think about this as formulating our null hypothesis. Okay, so after the principal has implemented this this program to encourage students to watch less TV, our null hypothesis is the hypothesis that the average amount of time spent watching TV has not changed. So that's going to be equal to the 21.3 hours. Okay. But then the alternative, which is kind of like the, I guess for lack of a better phrase, it's the hypothesis that we kind of want to occur, the one that we want to be true based on the experiment that's being conducted. And so if the principal has sort of implemented a program to encourage students to watch less TV, then we expect after that study has been conducted that the mean will now be less than 21.3. Okay. So if you think about this as a normal distribution, and we think about the mean as being right in the middle of the distribution, the area to the left is going to be less than the mean. Okay, so just using that logic, we think that this should be a left-tailed test because we have some suspicion that after implementing this program, students will be encouraged to watch less TV, so that value 21.3 might go down to the left. Okay, so we're gonna go ahead and check that. It checks out. Logic's out. Okay, so we're gonna move on with our lives. Let me go ahead and clear the drawing, and we'll go to question number 37. Okay, this says, the graph portrays the decision criterion for a hypothesis test for a population mean. The null hypothesis is that the mean is equal to the null mean. Okay, so that's what we expect for a null hypothesis, that the mean is unchanged. The curve is the normal curve for the test statistic under the assumption that the null hypothesis is true. Okay, use the graph to solve the problem. A graphical display of the criterion follows. So we have this graph here, and let's see, kind of highlight some things that are going on in the graph. So we have this area over here where we do not reject the null hypothesis. This is the region over here to the left. The region over here to the right is reject the null hypothesis. Okay, and it looks like we have some cutoff value here. Looks like we have some cutoff value at this value here, which is a z value. Which is 2.17. You might be asking me, why am I rewriting 2.17? I'm just trying to figure out what's going on here. Determine the rejection region. Okay, so let's see. Can I scroll down? not without messing up my drawings. Okay. So it says all z-scores that lie to the right of 2.17. Okay. Yeah, that makes sense. All z-scores that lie to the right, because that's the rejection region based on what we see here in the diagram. 2.17 looks like the cutoff value. Okay. All z-scores that lie to the left, that is on the left side of 2.17, well, that would fall over here in the region that says do not reject the null hypothesis. Okay. 0.015. Okay. Now that number was throwing me for a loop a little bit, but I'm thinking, let me go ahead and draw this real quick. This number seems really small, right? So if we think about like that 1.0 or 100% of the probability lies underneath the curve, then if I subtract this 0.015, okay, what do I expect to get? So I'm just going to throw that in the calculator really quick. Again, this isn't really doing anything for us. I just want to make sure I know what's going on in this figure. So 1.0, okay, again, there's a little dot here, 1.00 minus 0.015 gives us 98, 0.985. What I'm thinking that this value represents is the probability of, or the area under the curve on this side of this z-score, okay? Anyway, getting back to what this question is actually asking us to do. It's saying determine the rejection region. Well, clearly based on the graph, the rejection region is anything to the right of this z-score value, which is 2.17. So I'm just going to go ahead and Hail Mary this one. That should be correct based on everything that we've talked about. And it sure is. We got that check mark there. Okay. So we can move on with our lives. That one should have been just a straight read from the graph. Okay. And it clearly indicates that the rejection region is over here to the right of this z-score value. Okay. So we're going to move on with our lives and go to question number 38. Another wordy one. So let's go ahead and dig deep and read this problem. It says, the National Weather Service says that the mean daily high temperature for October in a large Midwestern city is 59 degrees Fahrenheit. So I'm going to go ahead and just highlight some stuff as I read, just so that I don't get fatigued. So this said that the mean daily high temperature for October for a large Midwestern city is 59 degrees Fahrenheit. Okay. A local weather service suspects that this value is not accurate and wants to perform a hypothesis test to see or to determine whether the mean is actually lower than this value. And the operating word here is lower. Okay. A sample of mean daily high temperatures for October over the past 36 years yields a mean of 57 degrees Fahrenheit. Assume that the population standard deviation is 5.9 degrees Fahrenheit. Perform the hypothesis test at a 0.01 significance level. Okay. So let's think about this. First of all, let's set up our null and our alternative hypothesis because there's a lot going on here. I'm going to switch colors over to black, and we're going to think about our null hypothesis as the hypothesis of no change. Okay, so H null is equal to, let me back up. We say that H null is that the mean mu is equal to 59. Again, that there is no change from what the National Weather Service reported, 59 degrees Fahrenheit. The alternative hypothesis, based on the local weather service, they think that based on data that they're collecting, that the mean mu it's actually going to be less than 59 degrees Fahrenheit. Okay, so just bear with me as I type or as I write this out on the screen. Okay. So what we need to do is think about what they gave us here. So I'm going to write down some of this information and we'll switch over to the document camera so we can sort of think through this problem. I have kind of a normal distribution, okay? And we're thinking that the mean here, mu, is equal to 59 degrees Fahrenheit. The population standard deviation, sigma, is given as 5.9 degrees Fahrenheit. Okay. And we want to perform a a left-tailed test. Okay. To see if we get a statistically lower temperature value or mean daily high temperature. So we're looking for some cutoff region over here on the left side. So this is going to be our cutoff for our left-tailed test. Okay, so let me go ahead and switch over to my document camera so you can see what I'm drawing. Okay, now they said that we want to perform this hypothesis test at a significance level alpha of 0.01. So we want this probability, alpha, this rejection probability over here to be 0.01, okay? Which means that the remaining probability over here is going to be something really high. So if I had just 1 minus 0.01, then 99% of the data is going to fall in this region over here to the right. But we're concerned about seeing about getting a value that falls over here. Okay. So what we want to do is do a significance test, but we can find this cutoff value here by going to our calculator. And then we can type into our calculator second distribution, normal CDF. Our lower is going to be -1 E99. Our upper is going to be, actually we need to find this value. So that's not the function we need to use. We need to use, where is it? Inverse norm. Inverse norm. So the area is going to be 0.01. And then our mean is 59. And the standard deviation is 5.9. Okay. So that should be 45.275. Okay, I'm just going to go to 4 decimal places. So that's going to be our cutoff value. Okay. Okay, but if you look at the answer choices here, this is going to be we're going to need to frame this in terms of a z-statistic. Okay. So we could transform this into a z-statistic by simply doing our z-score transformation. Okay. So what we can do is, I know this is going to be changed to 0. We can do this value minus the mean divided by this number here. Okay. So if we want to get our z-score for our z-score cutoff, we can do 45.275 minus 59 all over 5.9. Okay. And that's going to equal something. So let's go ahead and just do that. Minus 59. Divide that by 5.9. Negative 2.32. And I'm going to go with 32. 6. Okay. So we can think of this as being our cutoff value. So if this is our cutoff value, then that's going to be close enough to negative 2.33. Okay, so is that enough information to distinguish what we're looking at here? Okay, well, let's take a look at Alex again. Okay, so it looks like we are conducting we said our null hypothesis is that the mean daily high temperature is equal to 59 degrees Fahrenheit, and we are conducting a left tail test. So actually, right away, we could have seen that this first option is the only one that sort of frames the hypothesis in terms of a left tail test, because it already said that whether the mean was actually lower than 59. So that one's good. And since those are our only two answer choices, we don't really have to go any further. I did sort of show us how we got the critical value there. So the test statistic is already given here. The critical value we obtained, but that's equal to what we're showing here. So we don't really have to think any more deep about that. We're going to go ahead and check our final answer there. Again, sort of spinning our wheels there a little bit. That's my mistake. I should have just stopped when I noticed that the two answer choices, one of them was the only one that was correctly framed with the correct alternative hypothesis. So we'll just move on from there and not think too deeply about that. So let's go to question number 39. This one says, what two things should be done before one performs a regression analysis? So we're looking to select two things here. One, construct a scatter plot. Well, that sounds like a good idea because you need to be able to assess visually whether or not there is a pattern, a discernible pattern in the data before you perform a regression analysis. Okay. Test the significance of the correlation coefficient. No, that's getting a little bit ahead of ourselves. Draw a curve, connect the leftmost with the rightmost point. No, that's not right. Find the measure of center and spread for each data set individually. Okay. Well, none of these really seem like great options here, but let's see. Test the significance of the correlation coefficient. I'm going to go ahead with that one because there's two things we want to do here. Construct this scatter plot so that we can determine whether or not there is a visual pattern. And then find the measure of center and spread for each data set individually. That might be helpful for some preliminary data analysis, but it's not really going to help you determine whether or not you should perform the regression analysis. Drawing a curve, again, just drawing a curve without having any reason to do so, we would have to construct the scatter plot first. And then there's no reason why we should connect the leftmost and the rightmost point, okay? Because that doesn't make any sense. There's going to be a lot of points in between, and we'd be ignoring all of those points. So I'm going to go with the first two options here. Just take a wild guess. If we're wrong, we're wrong, but we're not, okay? So the first thing is definitely always go ahead and make that scatter plot. So imagine that you have a scatter plot with stuff like this. Okay, that was kind of a large point there. Let's go ahead and put a point here, a point there, a point here, a point there. Okay, now this data is kind of arbitrary. Again, it's not real data. I'm just putting points on the screen. But right there, even just sort of squinting, we can see that there appears to be kind of a positive relationship between the X variable and the Y variable, okay? So because we have a visual idea that there's a relationship between those two variables, that one has an effect on the values of the other, then we might want to go ahead and perform a regression analysis. But then when we actually throw that data into the calculator, we're going to get an estimate for R, the correlation coefficient. okay? And that estimate is going to be some value that's going to be associated with a p-value, okay? The p-value tests the significance of that correlation coefficient. So if that p-value is less than 0.05, then that means we have a significant correlation between the two variables. At that point, we can go ahead and run the regression analysis and figure out, is there a, let's see, is there a straight line that can be used to represent sort of like the average relationship between the x and the y variables, okay? All right. Let's go ahead and move on to the last question there. And let's go ahead and pop back over to Alex. All right. So here we go, yet another regression analysis question. And this is our final question. So it says measles and mumps. The data show the number of cases of measles and mumps for a recent 5-year period. Okay. So again, if we can sort of piggyback off of that last question, we have our data, and it says that if we're sort of ignoring the table for a moment, it says the correlation coefficient for the data is R equals 0.678, and alpha is equal to 0.05. That's our significance value, okay? So if I'm going to annotate, if I'm going to draw on the screen, remember that the correlation coefficient is a value between -1 and +1. And so the closer that this value is, either -1 or +1, that means that we have a stronger correlation coefficient, okay? Again, piggybacking off of that last question, is this correlation coefficient significantly high or significantly low? Well, we need to test it to see, okay? And what I mean by that is we need to go into our calculator and actually perform this linear regression t-test, okay? Okay, so we're not really performing the linear regression because we're not going to go ahead and find the linear equation that describes the data. But what we're going to do is test the correlation coefficient for significance to see if it's even worth conducting that linear regression analysis, okay? So what we need to do here is test the correlation coefficient. So we have R is equal to -0.678 according to Alex. But what we're actually going to do is throw our data into the calculator. So we're going to put the measles cases in L1, and we're going to put the mumps cases in L2, and then just type in our data into the calculator. Okay, so I'm not going to bother with writing these down, but we have 49 is related to 817. Then we have 130, 61, 54, and 220. Why not just write down these values? 130 is related to 454, 2002, 2552, and then 388. So we can go ahead and go over to our calculator and go to stat, edit. Okay, we used these lists before, so I'm going to clear them, and you can feel free to clear your lists by clearing the entire memory. But I'm going to go ahead and type in the data for measles cases, which is 49, 130, 61, 54, 220. Then I'm going to move over to L2. I'm going to put 817, 454, 2002, 2552, and then 388. We've got to make sure that our lists are balanced. If I accidentally mistyped one of those numbers, it could throw off the analysis. But now we want to go to stat, and then we're going to go over to test. We're going to go all the way down until we see linear regression t-test. Linear regression t-test. Not linear regression t-interval. We want to go with option F. linear regression t-test, and we'll leave L1 and L2 alone. We'll leave this as a frequency of 1. We'll leave it as a two-tailed test, and then just calculate this. And all we're looking for is the p-value here. Okay, so when we computed our p-value, we got p is equal to 0.20862. Okay, so I'm just going out 5 decimal places again arbitrarily. If you want to round that off to 3 decimal places, that's fine. 2 decimal places, that's about 0.21. Okay, we wanted our p-value to be less than 0.05 because this was our significance level. But this number is greater than. This is greater than 0.05. And since it's greater than, that means that this is not a significant correlation, not statistically significant. Okay. So that's going to help us answer this question because we don't have to do additional work of actually going through a regression analysis if we don't have a significant correlation coefficient. Okay. So the correlation coefficient was allegedly negative 0.678. You can verify that in the calculator. And the significance level was given to us as 0.05. Our p-value was not below that threshold. So should the regression analysis be done? No, the regression analysis should not be done. Okay, and that's going to save us some time because in the universe where the p-value is good and we should do the regression, then we'd have to do some additional work. But for that one, we're just going to go ahead and check. And we're done. Okay. So hopefully this has been a thrilling experience. I know it's been a thrilling experience for me to make these videos for you guys. And I hope that these things are helpful for you. If you need to speed them up, I know that sometimes I can be a little bit wordy in these explanations. Please speed up the time on YouTube. And if you need to slow down or pause, make sure you're slowing down or pausing to make sure that you understand what it is I'm saying. Okay. Best of luck to you guys with your final exams. And hopefully you guys will be able to move on to bigger and better things after this. So take it easy and good luck.